Um, well, welcome everybody to this ASDI data informational session. Today, we'll be talking, actually, before I proceed, let me ask, since we have a lot of people on the call, if I could ask people to mute unless you're talking. We will be having a period of Q&A towards the end of this session. So if you have any questions that show up along the way, feel free to add them to the chat area, and we'll try to address as many of those as possible by the end. But first, let me just welcome everybody, and thank you for joining us today. We've been planning this for a while, so we're excited to get this going and have the opportunity to bring the experts about the CMIP6 data to this session. So I'm Anna Privet. I'm the program lead for the Amazon Sustainability Data Initiative. And I'll tell you briefly about this program in a few seconds. But I sit on the sustainability side at Amazon. And also on the call is Zach Fleming, who is the technical lead for the program. It sits on the AWS side of the house. We have also a set of speakers that will join us today that are representing this broader collaboration or partnership. So we've been working very closely with the Earth System Grid Federation, in particular the GFDL group, and Balaji is online. Thank you very much for joining us. And also with the Pangeo project. And so we'll be hearing about this group, specifically about the data that is stored on AWS and now available to the community. So let me just say a few words about ASDI to set the context for this collaboration. So ASDI is the Amazon Sustainability Data Initiative. As I mentioned, is a tech for good. And basically what we're trying to figure out is how to leverage Amazon's scale and our technology to really help advance the space of sustainability and remove the technical barriers and reduce the cost and the time that it takes to analyze big data sets, acquire them, and analyze them to generate insights for sustainability. What we're trying to do here actually requires a bit of a change of the traditional approach of doing science. So we know traditionally we've been taking the data, moving into close to the individual researchers around the world. And as you can imagine, there's a lot of constraints there. On one side, there's multiple copies of the data. There's an obvious, from a sustainability point of view, an obvious carbon footprint issue, but more related to the usability of the data, what we've seen is that the use of data sets like the CMIP and others that are extensively large really create a barrier for most people to be able to use the data, acquire it, store it, and analyze it. And that effort is being repeated over and over again. So what we're really trying to do here is leverage the value of the cloud, and in this case, the Amazon S3 buckets, and work to the extent possible with the data providers, bring the data to the cloud, create some authoritative versions of the data that have become available to the community, and really encourage people to come and build the analysis in the cloud by leveraging a lot of the services that are available, in this case, on AWS. So we built this program focusing on 3 core pillars. The first one is focus on the democratization of data. And I guess that's what we're trying to do here, is identify what are those foundational critical data sets that are really relevant to advance the space, like climate sciences or climate resilience or food security and others in the space of sustainability, and really bring those data sets to the cloud and make them more broadly available to the world. The compute component of the program is focused on enabling access to compute. Obviously, the data is great, but by itself is not really helpful. So how do we encourage people to actually use the compute and offset the cost of that experimentation? And so I'll be mentioning in a second, but we have a dedicated cloud grant program or budget that we have allocated to sustainability projects, and we have an open call for proposal, and we really want to encourage people to come and use it for this particular data set. And then the third component, not less important, is recognizing that we can move faster if we work collaboratively, if we share our knowledge, if we share best practices, what's working and not working. And so the program is really trying to develop a lot of mechanisms to encourage that, for people to write tutorials and host sessions like this one, where we create an exchange of knowledge and communication between the users and the providers of the data. We have a series of blog posts to demonstrate the art of the possible and other things. So I just represented here what are the things that we in general will provide to the community. Of course, there's this this catalog of data, the ASDI data catalog, as part of the bigger open data catalog that we have on AWS. We have tagged all the data that we believe is of value to sustainability. We have now petabytes and petabytes of data, anything from historical weather records that we are getting from NOAA, for instance, and other data providers around the world, climate projections, satellite imagery, air quality. So please go and visit. There's an extensive amount of data there. Another resource available is this opportunity. If you have a valuable data set that is really of value to the broader community, we have this AWS Open Data Sponsorship Program that we use to support ASDI that basically will cover all the costs of storage and egress costs associated with distributing your data in the cloud. The model we use is that the data remains as part of, so the data provider retains all the control and ownership of the data, and they are the ones distributing the data in the cloud. We basically subsidize the costs related to the storage and the egress. So that's on the data side. On the compute side, we have this, as I said, this dedicated cloud grant, which I'll talk more in a second. And then this is all active links, and we'll share this with the community, but you can also visit our webpage, amazonsdi.com, and have access to all this information. The bottom one is really the information that we are encouraged the community to share with each other and the resources that are available. So let me just give you a very quick overview of this data set in the cloud. So if you would go to the registry of open data on AWS, specifically to the ASDI or Amazon Sustainability Data Initiative portion of it, you would find the data set. In this case, the couple model intercomparison project 6. There's, as you can see, other data sets that you can explore. And once you open that page, there's a series of different types of information there, and you can explore on your own. But just to give you an idea, there's a general description, an update on the frequency, and this information is available for all the data sets we have available in the cloud. The license, we primarily work with data sets that have an open license, so anybody can use them even for commercial purposes. Some documentation. In this case, the data is being managed by their System Grid Federation and by Pangeo. And then another portion to the right of your page, you will find information about to actually access the data set on AWS. In this case, because we are making the data available in 2 different formats, in the native NetCDF and also in ZAR, you would have the chance to actually access the data from those 2 different buckets, and you have more information there about it. This portion of the landing page really exposes the information that the community is making available, and some of it is actually our own internal team. Zach and others have been creating tutorials to help people use the data, and I know Pangeo and the GFDL team has been working on this as well. So please feel free to submit through GitHub additional resources that you believe are of value to the broader community, and we'll add to this page. And then this part here I wanted to mention in particular because we're trying to figure out whether the initial amount of data that we put in the cloud, which was selected based on what we believe were the needs of the scientific community, are really meeting those needs. And so, as you know, or you might know, the CMIP data itself, it's a huge amount of data, and so we have been selective in what portions of it, what variables and models we move across, but we are really open to getting feedback from the community to understand what are the things that are really useful. So we have a couple of links here. If you have technical questions, please direct those to Pangeo, but if you are interested in letting us know what's working or not with the data that is available out there in terms from a scientific point of view, whether you want additional data sets. And if you want to let us know how you're using the data, we would like to highlight those in presentations and publications we will make in the future. So we're very open to your feedback and eager to get it. Okay, last thing, and I promise we'll get into the main relevant part of this conversation, but I wanted to mention that we are really excited to have this data in the cloud. And we're doing this, I mentioned, to basically enable the community, hopefully, to get access to the data and use it. So we really wanted to encourage and offset the cost of using the data in the cloud for those that are interested in. So through this open call for proposals, we would like to create a dedicated vein for this data. So we will be prioritizing evaluating proposals that come by November 15th. We have a preference in general for work that is that could support developing countries or advanced climate sciences, but we'll be open to any kind of proposals. And the application is fairly simple. The link is there, and we can share it again at the end. But the idea here is that we need to know what problem you're trying to solve, how the cloud is going to be part of that solution. And then we would like to see that you're going to share that with the community, in some way. We really want to share this information. Make sure you mention that you're using the CMIP6 data as a way for us to prioritize the evaluation. And on that point 4, we're asking if you have any future work in the cloud. This is not required in any way, so don't feel like if you don't have any plans, you shouldn't apply. It's mostly for us to have an idea how this fits in bigger plans that you might have of working the cloud and connect dots. Okay. I'm about to end. I just want to mention this. There might be of value to this community. We recently supported a collaboration with Silver Lining and NCAR to run the first climate model full production in the cloud. They're currently doing that and producing the data. The model and the data will all be made available to the community as soon as it's available. So this is just part of that idea of trying to democratize more access to the data and the model and encourage more collaboration. So keep an eye on it if that's of interest to you. And now I am going to pass the floor to my invited speakers today. I'll let them introduce themselves. They're coming from different organizations that have been part of this collaboration, and I'm really grateful for the opportunity to have them here and for all the work we've done together. So let me pass the ball to, is it Aparna? Are you going to take the lead?
Yes,
okay,
yes. Thank you so much, Anna.
Yes, so feel free to steal the screen from me now.
Okay, all right. So Chris is going to be presenting. All right.
Okay.
Let me put this in a full screen.
Okay.
All right, can you see that?
Yes, I can see it.
Excellent.
Great. So thank you so much, Anna, for that wonderful overview about ASDI. I think it set a nice tone for my overview here. I'm just going to be expanding upon a few points that Anna hit on. My name is Aparna. I'm affiliated with Princeton University and GFTL. Today, I will be presenting a project overview on behalf of both the ESGF and Pangeo community. We have 3 more speakers lined up to give you an interactive demonstration. Next slide, please. First and foremost, I want to emphasize that previous slide, please, Chris.
Yep.
Yeah, there you go. Thanks. So special thanks to each and everyone listed here. This is clearly a community-driven effort, and I want to acknowledge all the groups listed here. Next slide, please. In terms of motivation, what else could be motivating than the very nature itself? Suki Manabe, he won the Nobel Prize for Physics. Manabe did a study along with Weatherall in 1975 that showed the effects of the doubling of carbon dioxide on climate using general circulation models. This, along with 4 other models, were featured in a scientific assessment report, what's also called the Charney's report, and published in 1979. This sort of laid the fundamental basis for what the IPCC is today. IPCC is a United Nations body. It stands for Intergovernmental Panel on Climate Change. This figure that you see is the global temperature change all the way from historical to the projected future scenarios under different emission concentrations. Now, what does this say and what does the impact actually feel like? There are several headline statements that's been documented by IPCC. One thing that struck me is that the severity of the dry and the wet events are only going to intensify. So we'll probably see more such events that I have here in the slide. In terms of mitigation options, IPCC also documents a summary for policyholders. For example, United Nations has about 17 sustainable development goals, what you see in the rightmost picture here. IPCC in the policymaker summary provides a nice correlation and linkage between the mitigation options that they lay out and the sustainable development goals. This, I think, is very useful for the community in general. Next slide, please. In terms of what data actually goes into the IPCC reports, they all come from what's called the Couple Model Intercomparison Project. We are in the 6th phase right now, and the circular diagram that you see on the left here is the experimental design for CMIP6. In the center, what you see is the DEC. DEC stands for Diagnostics, Evaluation, and Characterization of Clima, as in climate. DEC and historical together are sort of the core experiments for CMIP6, or sort of the entry 6 if someone wants to enter into the CMIP6. There are several objectives for CMIP. The main ones are that we want to see how the Earth system models respond to forcings, such as greenhouse gases. Also, we want to study about the origin, characterization of systematic biases. Not just this. So overall, CMIP helps us to better understand not just the past, present, but also the future climate change. In terms of the powerhouse that actually makes the data available to the public from modeling centers all over the world, that powerhouse is called the Earth System Grid Federation, or also often known as the ESGF. This is an international collaboration that provides data from several climate assessment reports. IPCC is one of those. The nodes listed here in this diagram can be considered data nodes spanning across different countries, not just one country. Next, please. In terms of challenges and our path forward, we're talking about data that's in the order of petabytes, only considering CMIP6 in ESGF. There may be other projects too. And the data that we see are all apples and oranges, or mostly apples and oranges, different experimental design, model output formats, and such. Third biggest challenge is that we have numerous science questions. I mean, we literally have a fire to put out. In terms of path forward, accelerating research, is there anything we can do to accelerate research? Could we do more computational processing that's parallel? Could we do something where the scientist focuses a little more on the science aspect and a little less on the data access and the downloadability aspect? If you see the picture to the bottom rightmost corner, you see that we have diverse groups of CMIP6 users all over the world. And this can definitely be improved. So as Anna mentioned, could we democratize access to climate data? In one way, could we bring our analysis closer to where data lives rather than moving data around? Next slide, please. This is one initiative that I want to highlight. We're talking about CMIP6 data that is going in the cloud. We have both the NetCDF and ZAR datasets, CMIP6 collection in AWS S3. The links here take you to where the data is actually there. And all of these references are also pointed to you in the CMIP6 registry page, or the landing page that Anna also pointed you to earlier. ESGF World is the name of the NetCDF bucket, and the CMIP6 PDS is the name of the ZAR bucket. There are several ways one can, try out or look for what data is actually in these buckets. One is if you just follow the link that says indexed, ends with index.html here. Sorry, I'm not able to move my mouse pointer here. It takes you to the AWS S3 Explorer. And there are also other ways to look at the data. If you want to look at it programmatically and also analyze your data alongside, you can also check out the intake ESM catalog. We'll see about that in just a bit. If you're a Threads user, you can use the Threads catalogs for the NetCDF datasets. Similarly, for the ZAR datasets, the intake ESM catalogs are available for you. We are also working towards the spatio-temporal asset catalogs, also known as the stack catalogs, and that's underway. Also, please note that the ingress and egress is free for these buckets. One other important pointer, if you go look at the CMIP6 registry in AWS, is that you will find information on how to appropriately cite CMIP6 data, and we consider that extremely important for this work. Next slide, please. Now, in terms of community-driven practices, it's very clear that without best practices and standards, it's very hard for us to improvise and automate certain things. For example, something to do with data exploration. The blue text that you see here on the left, it's a path to an object in the bucket. Really, you can deduce this path because the community actually works towards what's called the directory reference syntax, or DRS, that makes this very easy. And each of these values that go into those individual directory structures, or really prefixes in object store, they also adhere to what's called the control vocabulary, CMIP6 control vocabulary. So what do you do with this, right? You are able to automate APIs that can actually generate these catalogs, which can feed into what you see on the right-hand side. For example, this is a quick usage of an intake ESM package, which Julius will also touch upon later. So when you use the search function, you can quickly query, what type of variables or what data sets do I have in the cloud that match a specific criteria. If it's all Atmos monthly, I say table ID is AMON, for example. And if I just want to look at all the historical simulation, I plug in experiment ID set to historical. That's another example. I also have all of these links that are here, hopefully helpful to you, and will be shared later. Next slide, please. We also have many other initiatives that will be of great interest for you. What do we mean by Earth System Grid Federation in the cloud? That will be led by Chris Rand next. And if you want to generate an analysis-ready cloud-optimized data set, could you do that? Charles Stern will tell you about that. And if you have a multi-model CMIP6 analysis and you can't wait to speed it up, Julius Bosecki will throw some light on that as well. Thank you so much. With that, I will turn over to Chris.
Thank you, Aparna. So thank you, everybody. Basically, I wanted to get started by the notion that, since we're putting the CMIP6 data in the cloud, we wanted to focus on three main objectives when we had put this data in the cloud. The first is accessibility. So who can see the data? Data permissions, data uptime, the discoverability of the data, which was like tools to access the data for data analysis, the metadata and the user interfaces, and the performance of the data, which is how efficiently one can analyze the data, and with a focus of also a focus of scalability and related performance as well. So we want to provide an infrastructure that would allow us to promote a scalable framework, promote good data management, and also provide a good data metrics analytics. So the first thing we wanted to do is, for building our CMIP6 data node, is we wanted to utilize Amazon's Elastic Kubernetes service, or EKS. It allows us to run Kubernetes in the cloud, which in and of itself allows us to deploy and manage ESGF software services and then other related tools, but in a scalable way. So again, you can see sort of what EKS looks like in general here. This is a map showing our deployed EKS clusters. There are 4 of them, and I will get to each of these here on this slide. The first region, the Ohio region, US East 2, is our primary ESGF cluster, where we have 3 separate EC2 instances, and which has the ESGF data publication software installed and enabled, and also mounts the ESGF World S3 bucket of about 1 petabyte in space as a file system, and I'll get to the S3 stuff in a second. We have 3 other regions: a Virginia region, US East 1, which serves as sort of a dev test cluster for Jupyter Hub in data analysis, with 3 to 20 EC2 instances for auto-scaling. US West 2, which is also that's the ESGF dev test cluster, with 1 EC2 instance available, and it has been made to house the CMIP6 PDS ZAR S3 bucket that our Pangeo collaborators have utilized. And then there's also a Canada region that deploys AWS Fargate. So that is home to serverless containers and allows collaborators to test data sets accessibility. So getting to actual cloud storage, with our EKS clusters, we wanted to make sure we anchored the data holdings to a storage infrastructure that provided good security, organization, and efficiency. Well, enter Amazon S3, the simple storage service bucket. And as has been discussed before, we have deployed there's been deployed 2 buckets, ESGF World bucket, which houses a NetCDF data mounted to EC2 instances on the ESGF cluster, or with 1 petabyte, and the CMIP6 PDS bucket, which houses ZAR data, utilized on the EC2 instance for the on the ESGF dev test cluster, the US West 2, as I mentioned earlier. And it's dynamically optimized for performance and cost effectiveness on the server side, but free to use on the client side. It has data security policies enacted as 3 bucket policies, and objects are organized compliant to the CMIP6 DRS structure, again, which Aparna mentioned earlier, 2 petabytes total between the 2 buckets as of now. So here's sort of another diagram of how our cluster, our ESGF cluster, is associated with the ESGF World, and how the ESGF software stack can be utilized on our system. So the EC2 instances, as I said before, mount the S3 bucket using a POSIX-like file system, which is known as Goopies. There are others out there, but we chose Goopies because it's high performance, easy to set up. And the reason we wanted to, the reason actually we needed to use this file system is that the ESGF software stack alone in its current state cannot directly interact with the S3 buckets. So it needs like a file system in order to go through its steps of publication. So that's how we got to set up Goopies and getting everything deployed. This is a figure courtesy of Phil Kershaw. This is just another view of what the what the Kubernetes cluster looks like today. One section of the cluster has the search, and other houses the web server metrics and searching, etc. So once we have set up the infrastructure, we wanted to focus on making sure we fill our S3 bucket. So how do we do that? Well, the first way we do it is we did a transfer of about 650 terabytes of high-value CMIP6 data sets, primarily based on the IPCC chapter variables and a consensus within the community. That took period over the course of about 6 months. And as it stands right now, we have about 665 terabytes in our bucket, and are willing to ingest even more data into that bucket, which I will talk a little bit about earlier. But yes, this was an initial data transfer to our buckets. So once we filled our bucket, we wanted to make sure we actually had people be able to access data from the ESGF World bucket. So in order to do that, we utilized the Threads data server. which is a web server that provides metadata and data access for scientific data sets. And it uses OpenDAP, OGC, WMS, WCS, HTTP, and other remote data access protocols. And you've seen this before, but we set up ESGF IO domain, which houses this catalog that anybody can take a look at and browse through threads. So in addition to threads, we had set up in collaboration with our collaborators, the ESGF data publisher, which runs through Goofies and is able to publish data in a way that once it's run, it processes the data sets, each individual data sets, into a record that becomes visible to applications that can utilize the ESGF search API. And one example I use is the Cinda tool, which is a software originally developed by IPSL, but also developed by folks from Lawrence Livermore and other collaborators. It further enhances the publishing further enhances discovery capability by enabling a bulk search for dataset parameters and uses dozens of available dataset metadata fields to even more further enhance discovery of the datasets. And I just put down here as the publisher is decoupled from the main ESGF software package. There's a greater flexibility for data egress. And So the next steps for our node is to get it federated with the ESGF network. And basically what that means is that we could basically, have it as a drop-down in the data node panel across multiple ESGF data and index nodes. It will allow us to have more data sets. With the publishing of more data sets by the ESGF publisher, we're able to make the data everything more available and discover. Again, it's another way to increase discoverability of these data sets in the bucket. Currently, this is sort of what the user interface is looking like, but in the future, there is going to be an updated user interface, I believe, called Metagrid that perhaps some other speakers can talk about later. But again, that will promote even more discoverability for our data.
And Chris, then, the transition, please.
I'm sorry?
I was just trying to say that, we have, in the interest of time, could you move towards the transition?
Okay, yeah. So, some of the next steps, we're trying to fill our bucket faster. Again, using Cinda as a way to further ingress to our bucket, and then utilize the ESGF network itself, which is 11 petabytes versus our initial repository of 650 terabytes. And we have a proposal submitted to actually expand our bucket to another 3 petabytes for 1.5 petabytes for each bucket for a total of 5 petabytes. And after the talk, we have a comparison tracker of the 2 buckets that you can go to at the link described below. And then finally, I just wanted to get to this is the future architecture, sort of an outline of what the ESGF node future architecture will look like in the future with Stack Search and Elasticsearch in a separate Kubernetes cluster. And with that, I will turn it over to Charles. Thank you very much.
Thank you, Chris. My name is Charles Stern. I am a data infrastructure engineer with Columbia University's Lamont Doherty Earth Observatory, and I'm just going to transition over to a notebook to share with you so that I can share a bit about a project we're working on as part of the in connection with the Pangeo community. Excuse me, sorry, this happened when we were practicing earlier that it took a minute for this sharing to stick. Okay, hopefully this is going to stay now. So I'm going to tell you briefly about a project called pangeoforge, which is a tool for transforming archival data into analysis-ready, cloud-optimized data stores. The slides are available, and this notebook is available at the link that you see here. So we're actually not going to use a CMIP6 example here for two reasons. First of all, I want to highlight the fact that this is a generic tool for earth science data sets, weather, ocean, or climate data sets. That would be the first one, is that you can use this for really a lot of different purposes, including CMIP6. The second reason we're not featuring CMIP6 is that this is a very new tool, and this tool has not actually been used yet for transforming some of the CMIP6 archives under discussion today, but we're hopeful that, as others have mentioned, as this effort continues, that this will be able to accelerate our efforts considerably. So the data set we are going to look at is the optimum interpolation sea surface temperature data set from NOAA. So those of you who have tried to access some scientific data from federal agencies like NOAA in the past may be familiar with something like this. This is the HTTP index for this data set. And as you can see, this is sort of organized where there's a top-level directory accessible over HTTP. And then there are subdirectories divided by year and month. And then within those monthly subdirectories, there is a specific netcdf file for every day within that month. So if we were to kind of approach this in what we might call kind of the legacy way, we can use a utility like wget to download one of these files. Actually happens quite quickly. They are compressed at about 1.6 megabytes each. And then we could open one of these files using Xarray and take a look at it. So in the in-memory state, when it's uncompressed, it's about 16 megabytes for one time step here. And you can see that has a few different variables in this data set, including the sea surface temperature, SST. But the problem with doing kind of data at scale is that we would actually be interested to look at, say, like a very long time series from 1981 until 2021 on a daily basis. That would be a tremendously large number of files. That's over 14,000 files, and in memory, that's approaching 240 gigabytes in size. So that would take a very long time to download, number one. Number two, once you had it downloaded, it's not necessarily situated in a way that makes it easy to work with or easy to run computations. So a better way, which we're proposing, is this Python package that we've developed called pangeoforge. Within that, there's a module called, a sub-package called pangeoforge recipes, which contains the logic for transforming archival data sets into consolidated analysis-ready cloud-optimized data stores. In this case, we're going to discuss the ZAR format. I'll get to the ZAR format in a moment. But first, I just want to highlight what a recipe is. A recipe is sort of the core unit of contribution and activity in pangeoforge. And this is a Python file or a Python module, using the Python jargon for a file right there, is like a recipe is a Python file which can see all of the source files for a given data set and knows how to arrange them into a cohesive whole. So I've already made a recipe, and we've done a recipe for this sea surface temperature data set. Briefly, that recipe is available in the repository for this talk, and you can see what it looks like here. It's about 20 lines of Python code, and essentially what it does is it abstracts the file path for that data set into a format that then can be used to generate arbitrarily any of the files needed, and then sets up a way of concatenating them or arranging them in the necessary way to make the cohesive data set. So if we just import that module into this notebook and take a look, what we'll see is that we have generated all of the URLs required for that data set. This is just a snapshot looking at the first, second, and then second to last and last files in that data set. And you can see that they're organized and indexed correctly, so that when they can be transformed into a cohesive whole, the algorithm knows how to arrange them. So what are we going to arrange them into? Well, right now you've heard mentioning some others speakers mention the ZAR format. The ZAR format, which you can read more about here on the documentation, is a compressed n-dimensional array data format, which provides chunking of those arrays, which is helpful for parallel computation. And importantly, it supports a high degree of concurrency or parallelism in your reading and writing, which makes cloud-based science a lot faster from a computational standpoint. In order to build a ZAR store, and this is the logic contained within this package, pangeoforge, we take the netcdf files and cache them if they're not already on the cloud. If they're from a HTTP server like we saw before, we cache them onto the cloud, write a sort of skeletal framework for this data set, and then write all of these chunks across into that ZAR framework and consolidate the metadata for the entire data set, no matter how large it is, into a single lightweight JSON file, which is then easy to read and introspect. Very briefly, the recipe itself sits in relation to a larger infrastructure here, some of which we've already seen in this presentation. We have some sort of a traditional data archive, which might be over HTTP, FTP, or some other web protocol, which transfers source data into a compute infrastructure for pangeoforge, and then that translates the data into an ARCO format, analysis-ready cloud optimized format, such as ZAR, as one example, and puts that into a cloud bucket. The user can then access that and discover it through a catalog. And very briefly, and this is just wrapping up here, what I have here is showing you the actual way to access, in this case, that same sea surface temperature data set, which is stored on our Pangeo S3 bucket here. And that has already been built. It's gone through the execution process shown in the flow chart in the previous slide. And we can see that we can actually open this data set quite quickly at a size of 241 gigabytes in memory. And unlike the single time step that we saw before, we now have in excess of 14,000 daily time steps available to us instantaneously. Now, if we were to have done this in the old model, we would still be waiting probably on maybe, the 50th file or something to download. But here we have access to all of this data at once. And importantly, we have a provenance chain. Because there was a recipe, the module that I showed you a moment ago, that describes the mapping between the source archive and that ZAR store on AWS S3 storage, future downstream scientific users like Julius, who's going to present in a moment, know the entire provenance of how that data set was transformed. Of course, whenever you transform any data, there is a risk or the possibility that something will be done that corrupts the data or makes it in some way less suitable for scientific analysis. And so by providing this link here, we're hopefully building confidence in the suitability of these optimized data sets for to meet the scientific standards for which they are used. So in conclusion, what you can do today to get involved in pangeoforge is start working on a recipe for a data set that you're interested in. And here's some documentation, a link for doing that. You can also open a pull request to the repo linked here, which is how we're going to manage contributions of these recipes to be executed on our shared infrastructure. And in the short term, if you have a smaller recipe, you can also actually just build that yourself to your own storage location if you'd like, using a notebook. And very soon, the automated bakery infrastructure will be available, and we'll start ingesting these recipes that are contributed. And we will also have a stack catalog. Aparna mentioned the spatiotemporal asset catalog. There is a very rough draft of that at this link here. which should not be taken as representative of where it will be quite soon, but very soon we'll be able to link to a wide range of cloud-optimized data sets through that catalog. So with that, I'm going to hand it over to my colleague Julius, who's going to show us, how all of this actually translates, I believe, into science, cloud-based science. So Julius, over to you.
Thank you, Charles. Can everybody see this?
Yes.
I'm assuming yes. Okay, good. So I'm going to try to be quick here to allow some questions. Basically, I'm looking at this from a user perspective and sort of the trying to describe what we're as a scientist, what I and many others I think also do with that kind of data. So the CMIP6 archive is huge, and this is just two of the so-called facets of data sets. But basically, you can imagine there's about 88 models. They all have sort of different code grids, physical, chemical, biological parameterizations, and then there's members in most of those models that have sort of slight differences in the initial conditions or the physical parameters, et cetera, et cetera. Basically, there's sort of a big matrix of n-dimensional data sets, and if they're sort of full depth data sets, they can be 4-dimensional. But what sort of scientists, I think, at least for the most part, want to do with these things is take all of these models and then really sort of run a custom analysis to each model or each member, or a custom combination of these, and then come up with plots that look like this. This is the same plot that Aparna showed before, the global temperature change. So in pseudocode, something that I think everybody wants to do is something like this. You just go through all of the data sets, you have your amazing analysis, you apply it, and then you plot the results in a very simplified way. However, the data that is in the CMIP6 archive is not quite there yet. There have been lots of efforts to really sort of consolidate all of these different models that come from very diverse sources, but there's still some cleaning up left. As you can see here, some of the data sets, for instance, for the horizontal, zonal and meridional index dimensions, they have different naming. On the right part, you see sort of a data set that is cleaned up with the packages I'm going to present here. So basically, this is sort of the old way of doing this. I found a lot of those code blocks where you end up having more and more if and else statements in there, which is sort of buggy and can lead to problems. And also, I think as others have pointed out before, really sort of takes your focus away from the science and puts it to the technical part. And I think that's not the right way to go. So that's why I basically started trying to sort of crowdsource these fixes and put them into a custom preprocessor, which is sort of right now the CMIP6 preprocessing package. Really quickly, why you want to use that? I think the first is sort of based on the X-ray data model, which is very flexible and very sort of ingenious for sort of getting scientific analysis done, because it labels n-dimensional arrays, and sort of for other people who might be more familiar with pandas, it's sort of the pandas for n-dimensional arrays. Because it's built on X-ray, this CMIP6 preprocessing really sort of integrates with existing Pangeo stack. There's some to name here: region masked, XGCM, and XESMF. I try to keep it very lightweight and task friendly, and it does work great in the cloud, but it also works everywhere else we have X-ray. So this is really a big plus for me. This is not a cloud-specific tool, but it actually works great in the cloud. Just quickly, sort of the components of it are sort of generally the processing module is really sort of for dataset cleaning and homogenization or sanitization, as you've seen with the naming. And then the post-processing, I'm going to demo that in a second, is really sort of to combine these model data to sort of concatenated or merged X-ray data sets, for instance, with several members to suit your custom analysis. There's also other packages that I'm not going to talk about, but feel free to check those out in the documentations. Okay, then let me just quickly switch over to my demo, and I hope my DAS server hasn't died. Okay, so basically I'm running this on the Pangeo cloud infrastructure on AWS, and I'm just what I've done before here to save some time is get a DAS cluster, so we have some computational oomph behind this, and then basically I'm just following the steps outlined in the documentation and the steps outlined by Aparna really nicely. So I'm just going to briefly go over this. So we create an intake catalog with intake ESM, and then I'm selecting, just for demonstration purposes, a subset of models and the historical experiment, as well as the strongly forced SSP 5A5 experiment. The only thing that I'm adding here is a pre-process keyword argument that is basically loaded from CMIP6 preprocessing. That's the only thing that's different from the instructions, and that's passed to the toDataset dict method down here. And I'm creating basically two. Let me just start this. I'm creating two dataset dictionaries. One is with the sea surface temperature of a variety of models and members. Again, I restrict this to keep this a bit shorter. And then I'm also loading the horizontal grid area, which we need to properly weight that sea surface temperature to produce a global SST time series. And you can see here what Charles mentioned is sort of the near instantaneous access. We've loaded way over 100 data sets in a couple of seconds, and we're ready to actually work with them. I've worked on other systems where you work with NetCDFs, and it takes considerably longer. So now what we're going to do is actually go in the post-processing step, and these two, there's other functions available, but I'm just sort of for this special problem, I'm basically just parsing the metrics from one dictionary into the dataset dictionary, and then I also concatenate members. So our Xarray dataset now has an additional dimension which represents the members. Let's see. Sorry, this is a known bug. And so we need to wait a couple of seconds here. What this does is actually, it's purely based on comparing the metadata of these data sets to figure out which ones need to be grouped together. And it's written fairly flexible so that you can basically define your own combination functions if you don't find those provided by CMIP6 preprocessing too helpful. Let me just start the plotting because that takes a little bit. So we, in the interest of time, I'm just going to quickly sort of demonstrate what we've done here. So the additional area cell O is sort of a 2D array of cell area, and our surface temperature TOS here now has an additional dimension of member ID, which has 5 members. So we're having a 4-dimensional array here. If you would actually have a 3D, so depth variable, you would have a 5-dimensional array. And then let's come to the brunt of it. So this is basically, I think, as close as I'm at this point am to really sort of focusing on the science and just looping over all the data sets. Taking away some of these like plotting commands here, this is all we're doing. There's 3 steps. And again, I think this also illustrates how cool Xarray is sort of you're selecting a certain time frame here. And then we're just taking, defining the SST as a weighted average over the whole globe, average over X and Y. And what we're then doing for visualization purposes is actually taking an annual, that's not 2 years, that's 1 year, average. And we're ending up with a time series that has still a member ID dimension. And then we're just going to plot that. And you're seeing in the back of this, this is crunching through gigabytes of data. With a really nice sort of Dask visualization. And I hope in a little bit, we're actually going to see this plot, which, again, this is a very simplified version. Obviously, the plot I showed for the IPCC has some more sophisticated methods in there, but you could implement all of them in here, and you really don't have to worry about the data sets and the units and the naming. It is all sort of homogenized. And I dare anyone to produce this plot before, like with downloaded data, you would probably still wait for the data to actually arrive on your computer, and then you can figure this out. But yeah, so this is a plot of global sea surface temperature, and you can see sort of the models are color coded, and you can see that there's biases between these models, but also sort of the change of sea surface temperature globally has different slopes. And so this is, I think, sort of a simplified science question that could be answered really.
Try to wrap up to leave a few minutes for questions.
This is it.
Okay. All right. Thanks. Anna, will you handle the questions?
Yes. Well, thank you very much, everybody. It's really excited to see all this different tools and developments that are going to really help us accelerate the time from data to knowledge, which is really the goal here. So I would say we have a few minutes for questions. I would encourage people to write them in the chat. And then I know we have a few that maybe I can just cover the ones that were responded already for it might be for the little time we have, maybe just open the floor. If anybody has a question, please unmute yourself. And it might be chaotic for a little bit, but we'll figure it out. If it is, we'll add some order.
Hi there, can you hear me?
There's some in the chat as well, Anna.
Can
Say it again. Yes.
Is
Please go ahead.
Matthew Mislinski here from the Met Office in the UK. I really like the sort of the service you provided with Pangeo. It's been wonderful to be able to do some exploratory analysis while the system's available. My question is, how do you intend to maintain the data you've got? I'm responsible for providing a lot of the Met Office and UK data to CMIP6, and there are some issues with data that we've retracted that I believe you're still providing access to. I'd just be very keen to sort of engage with you on how to make sure that sort of data is properly curated and provided.
I guess this would be probably a question for Balaji or the team, or Christopher Aparna, or
I can attempt.
Follow up offline.
I can attempt. I mean, in general, I agree that it's very challenging to curate data, especially CMIP6 on the cloud or off the cloud. At least for our buckets, the Pangeo and the NetCDF buckets, we are trying hard to have a process that checks if there's old version data or new version data actually available for specific CMIP6 data sets, and make sure it's in sync. But we do not have any automated process that's actually checking that. Right now, we just have some on-demand or offline checkers that crawl through the catalogs and then compare with what versions are actually available in the ESGF, the newest, latest, greatest, and make sure we only show the latest versions in the cloud. Of course, this is something that we are checking, but as users, I would recommend you to go back to the original source and make sure you're using the latest version, and also do the cross-checking from a user standpoint.
Yeah, I was just going to add, to Aparna's comment that this has been on our minds for several months, in developing some tools that can track, very dynamically in the ESGF network, data sets that have been retracted or are continuously getting updated or modified for any reason. So tools, plans to develop tools that are in motion. But it's a good question for overall management of data.
Great, thank you. I'm going to go through some of the questions on the side. I see David Sterling has a question. David, are you able to unmute yourself and share for those that are not on the chime?
Yeah, can you hear me?
Yes.
Okay, good. Well, the main thing is, the licensing. You mentioned that everything was free and open access, although we've heard some things like IPCC had to get a blanket waiver to use the CMIP6 simulations, and of course we want to use them for the National Climate Assessment. And Ken Kunkel has already been working in the cloud there, doing some analyses and ensemble means and that sort of thing. We just want to make sure that we understand the licensing and what we can produce, what we can actually provide in terms of derivative products and everything. I understand they're all Creative Commons share-alike licensing, but some may or may not have that. So I'm just wondering if all the ones that have been put up on the Amazon cloud are sort of the free and open share-alike 4.0.
Yeah, thank you. I'll let Aparna or the team answer specifically for CMIP6. What I was mentioning is in general, the data that comes into the system and is exposed, it has to be open, right? But each one of them individually in their webpage has specific information about the licenses and any restrictions that might apply. But Aparna, do you have anything specific about CMIP6 that you can share?
No, I think both you and David really are aware of the Creative Commons share-alike license. The only thing that I would add is just to double check, always look at the header of the actual data sets that's been published. There will be some specification that is tied to the licensing in an attribute called further info URL. So while in doubt, I would say, always check that. But it's true that all of the CMIP6 datasets are supposed to be compliant with that licensing. So, we can open it out here in the public.
Okay, thank you.
Sure.
Thank you. I I shared my screen so I can put a reminder about if people are interested, because I know there were some questions about the ability to work with the data in the cloud. Yes, there's compute costs associated with if you decide to work with it in the cloud, and that's why we are offering these cloud grants that basically would offset that work. We traditionally support them for a period of a year, but feel free to reach out, and if you have, they're handled one by one, so we will analyze each one individually, and there's no cap in terms of the amount we support. So if it's justifiable, we'll support it. Okay, I can no longer, because I'm sharing my screen, I can no longer see the questions. So is there any critical one, or I'll open? I know we're close to closing this session. I think what I would suggest is that I'm sharing here the email account for ASDI. If you have additional questions that we weren't able to address, and I'm sorry we didn't have the chance to cover many, please reach out to us. We'll try as best we can to provide those to the panelists today and get those answered. And I guess I don't know if there's any final words that the team wants to say. I want to thank everybody. I really appreciate the time and the effort and this collaboration. Anyone else wants to say anything? Otherwise, we'll close the recording.
I just want to say a big thank you to you, Anna and Zach, on behalf of our Pangeo and ESGF community. Thank you.
Sure, thank you. Okay, everybody, thank you for attending. And we're recording this. We'll be making the slides and the recording available as soon as possible in the GitHub associated with